So good morning. So let's continue with the study of the air intakes or inlets. And more specifically, we were busy yesterday with the external flow. And what I have represented yesterday was, in fact, the front part of the engine that I'm considering from the section that we have called AI, so this is the section I, down to the section 1, so these are the lips, so the physical part of the air intake. And in front of this, I have the stream tube that is in cruise conditions. Let's consider today the cruise conditions, even if we know that there is another shape when we are taking off, from the section A down to the section I, the I-light area. And here, before the section A, we have a flow that is what we call a parallel flow, where we have an undisturbed flow that is only started to be disturbed from the section A. Of course, there is a certain mass flow rate entering here, and there is also a flow that is not entering into the intake. A flow that is doing something like this, a flow that is doing something like that. And we are interested in the study of this external flow, because the reason is that in the equation of the thrust, let's consider that the thrust is only along the axial direction of the engine, what we can call the direction X, so the direction 1x that we have here, oriented, let's say, positively forward. We have considered that it was the sum, a vectorial sum of R and FPA, R being the reaction of all the gases, air and combustion gases passing inside the engine, and the action of PA on the external side of the engine. And when we say the external side of the engine, this is from the section A down to the section 5. This is what we consider. And that means that in this definition, this is a choice that we have made. You could take another one, but you would have then other problems. There will be a problem at a certain moment. You are considering that everywhere the external pressure acting on the stream tube and acting on the external side, always perpendicular to the nacelle, to the walls, to the external cowl of the engine, that we have everywhere PA. And we have got the equation that we have called m dot v jet minus VA plus A5 P5 minus PA is coming from there. But if we look at what we have discussed yesterday, we see that through the shape of the external tube or the stream tube, what do we have? If you consider the part between A and I, here you have a decrease of the speed, decrease of the Mach number, an increase of the static pressure, and that means that the pressure here is larger than PA. So the pressure here, this pressure is P, and this is larger than PA. So that means that there is an overpressure compared to PA acting in this direction. If we consider that the system is axisymmetric, of course the vertical component will be, let's say, compensated over the 360 degrees, and you are staying with a, let's say, axial contribution a 1x contribution that is going into the opposite direction compared to 1x. And this is making something that you have to add to the thrust. And you see that it's in the opposite direction compared to the thrust. The thrust will be like this. So this is a negative thrust, and a negative thrust, we call that normally a drag. And so this section here between A and I is delivering a drag that we can compute considering the integration of P minus PA multiplied by the surface on what it is acting between the section AA and the section AI. And this is what we call the additive drag. The additive drag, which is a positive drag, which is a negative thrust. So we need to be coherent with the signs, of course. And the most, let's say, coherent method is to say that a drag is negative and a thrust is positive, for example. But also, there is another part of the flow, which is the part between the section I and the section 1. And for the part between I and 1, we have the flow that is, in fact, like on the suction side, on the extrados of a wing. And so there we will have a decrease. We have an acceleration of the flow, and we will have a decrease of the static pressure. And so if you compare to PA, let's consider that you have here PA. In fact, the pressure that you will have there will be lower than PA. And so there, P minus PA, because PA is our reference, P minus PA, it is in fact a contribution that is going outward, and that is, let's say, pulling your air intake outward. And that is giving, of course, a positive axial or longitudinal contribution. And so here, if you make the integration of P minus PA, so another P, of course, the local P, multiplied by ds between the section I and the section, let's call it A1, let's say when the flow is again cylindrical, and this is what we want to say when the nacelle is again cylindrical, this is what we say. This is what we call the lip suction thrust, and that is something that will be an opposite sign compared to this one. If you say that the thrust is positive, this will be also positive, and that will be negative. Of course, you can say that it's positive, then this one is negative, and this one is negative. Okay? So you see that there is somewhere a compensation between this new force and the other one, because one is of the opposite sign compared to the second one. Of course, is it this one the largest? That would be then positive, or is it this one the largest? Then this effect would be negative. Okay? Also, there is, in fact, a third force to be considered, because if you consider the walls that of the intake that we have called the coal, so coal written like this, or that you can call the nacelle, the engine nacelle, you will have also friction here against these walls, here against this wall, all over the 360 degrees. So that will be a drag, because this is a friction force, so that will be oriented towards this direction, that we can call d coal. That would be equal to an integral of all shear stresses that you have there, multiplied by a certain surface. And that will give you a drag. So in fact, there are 3 forces for the intake. 1, 2, 3 that we have not considered before. Of course, the choice will be up to you. Do you want to add this one to this? Do you want to add this to the aircraft drag? Do you want to add this to the aircraft drag? This is a decision that you need to take. Or do you want to make the sum of this and to add that and to add this sum to this term? This is up to you. This is what we will call the thrust drag bookkeeping that we will discuss later on. Now, there is something that we must be very clear with. This is that these 3 forces, in fact, they are quite different. Why are they quite different? This is because the coal that you have there, this is only related with the surface, and for an existing aircraft, this surface is fixed, the intake is fixed, the length is fixed, the port tour is fixed, the surface, everything is fixed, and this will be, in fact, only proportional with the Mach square. So with the local Mach that you have there, somewhere it will be related to the Mach number of the flight square, because the Mach here will depend on the Mach number of the flight, but it's independent of m dot. Whatever m dot, whatever the shape of this channel, you will have the same speed on the external side for the decoal, which may be some very minor differences, but it will not really impact the situation. Whereas for the pressure that you have here internally, so that you have on the streamline here externally, and the pressure that you have here, this will change depending on the mass flow rate, depending for a given VA, PA, TA, it will change with the value of m dot, because m dot will change the shape that you have here, and m dot will change the pressure here, and will change also the pressure that you will have on the other side. Okay? And so these 2 are proportional with m dot, are depending on m dot, and this is why we say that this term, the decoal, is called a throttle independent drag. It's a throttle independent drag. This is just depending on the flight Mach number, whereas these 2 are throttle dependent drag. This one is a throttle independent drag, and these 2 ones are throttle dependent drags. So depending on the position of the throttle. So this one is, let's say, easier to study than these 2. Apparently, okay? We need, of course, to look into the details to see how we can compute that, and for this one, this is, let's say, much easier. Of course, the coal will be taken with the full